You still should ask questions if you have anything relevant to the immediate slides. Okay, I strongly encourage you to ask questions. Okay, so today we will begin with singular value decomposition, or SVD. Outline: full SVD, then we'll do reduced SVD, geometric interpretation of singular value decomposition, SVD. Then we'll look at some properties of SVD, low rank matrix approximation. And related to this matrix approximation is this Eckart-Young-Mirsky theorem, and we'll actually do this theorem and proof for Euclidean norms. And then MATLAB Demo. Now, if we have time, I'll show you how image compression can be done using SVD. Okay, that will be a second MATLAB demo. Okay, so we begin with full singular value decomposition. Given a M by N matrix, and we'll assume that A is a tall matrix, therefore M is greater than equal to N. So this is the full SVD. This is what it looks like. U and then this matrix, sigma with a block of zeros below it, and then V transpose. U1 through UM are the columns of this matrix U, and V1 through Vn are the columns of the matrix V. This is what it looks like. Okay, this is the matrix A. This is the full singular value decomposition. Whites are for zeros. And so you can see that this block matrix, well, it depends on the notation. Sometimes I call it sigma 0, sometimes I call it just sigma for the whole thing. Okay, forgive me, but it should be clear from the context. So this is a diagonal matrix. And then we have several rows of 0 beneath. And this is V transposed. Okay, so if V1 through Vn are the columns of V, then V1 transpose until Vn transpose are the rows of V transpose. Okay, and so U is a M by M unitary matrix, and V is a N by N unitary matrix. Therefore, U transpose is the inverse of U, so you have these properties, and likewise, since V is unitary, V transpose is V inverse, so you have these properties. Now, sigma is this, the diagonal elements will be the lowercase sigma i's, and then they are arranged in this order. Sigma 1 is the highest, then sigma 2, then sigma 3, all the way until sigma n. And all of these sigmas will be greater than equal to 0. Okay. And furthermore, if A is a real matrix, then U and V will also have only real elements. Okay, and regardless of what kind of matrix you have, these singular values will always be positive and real. Even if this matrix were, I have to verify this, but I'm 99.9% sure. If A were to be a complex matrix, then U and V will be complex, but sigma will still be all real positives. And these are called the singular values. The first element is the first singular value, then the second singular value, sigma 2, sigma 3, and so on. Okay, these are the singular values of this matrix. Okay, proposition. I'll do this without proof, but every matrix has one and only one SVD. With one caveat. Now, you can swap the sign of a column of U. And if it's one of the first n columns, then you have to swap. You can, excuse me, did I use the word swap? I meant invert, that is take the negative. You can take the negative of any column of U, and if it's in the one of the first n columns, then you have to do the same thing with V, and you'll get the same A. In other words, the U's are a set of orthogonal vectors, right? Each column of U is a unit vector, and all the columns are mutually orthogonal. But you can take one of the axes, one of the U's, and flip it around, take its negative, and it will still serve as a orthogonal basis. It will still hold the unitary matrix property. Okay, and same with V. So that's the only caveat. Otherwise, every matrix has one and only one SVD. Okay, and in that SVD, remember that these will be in sorted orders, the sigmas. Sigma 1 will be the highest, and sigma n will be the lowest. Okay? Okay, now the SVD, the matrix A, can be expressed as this summation. Now, each of these terms, Ui, Vi transpose, is a matrix of the same size as A, M by N, but it will be of rank 1. Correct? So, A is expressed as a summation of n rank 1 matrices. And what can be the rank of A? Since n, as in New York, is smaller than M, as in Maryland, so it's a tall matrix A, therefore the rank is at best n, right, as in New York. Okay, and so let's do the proof. So this is A, I write the SVD, and then I express U in terms of the columns, V in terms of the columns, so V transpose is in terms of its rows, and this is my sigmas. Now I'll multiply the second and the third matrices here. Okay, so what should I get? Sigma 1, V1 transpose in the first row. Second row will be sigma 2, V2 transpose. The nth row will be sigma n, V transpose, and then I'll have a bunch of zeros. All the rows beneath that will be zeros, okay, in this product of the second and the third matrices. And here, U1 through UM, I'll retain for now, but I will insert a few more columns here. I'll explicitly show a few more columns, okay? So this is what I have. This is my U. I multiply the second and third matrices together. Okay, and now let's look at what's happening here. What happens when I multiply this and this? This is a matrix and this is a matrix. Well, they look like vectors. You can pretend that they're block vectors. Okay, so U1, sigma 1, V1 transpose, so that's sigma 1, U1, V1 transpose, plus sigma 2, U2, V2 transpose, all the way to plus sigma n, UN, Vn transpose, and then all these columns, Un plus 1 through Um, are getting multiplied with zeros. Okay, this gives us some ideas of how to reduce SVD. We'll see that later, but for now, let's focus on this. Okay, so this is what we get. Sigma 1, U1, V1 transpose until sigma n, Un, Vn transpose, and then a bunch of zero matrices, which we can drop. So this is equal to summation I equals 1 through n, sigma I, Ui, Vi transpose. Okay, we just proved this theorem here. A equals summation sigma I, Ui, Vi transpose. Now let's look at reduced SVD. We started off with this, correct? And then we got this, and then we did this multiplication. So what's happening here is I can, well, these un plus 1 through were getting multiplied with all zeros, right? So I can simply ignore this, remove these columns, un plus 1 through these columns from u, and drop these rows. Okay, and then what should I get is, well, this sigma 1 v1 transpose until sigma n vn transpose, this vector, and I skipped a step, I refactorized it into sigmas and v's. So this is what I get. Okay, now this matrix here, the u's are m-dimensional, m as in Maryland. But how many columns do we have? Excuse me, how many, these are the columns. We have n columns, right? And each of them is a m by 1 matrix. So this is a m by n matrix this time. Okay, it's a tall matrix. This is now a square diagonal matrix, sigma, and this is still, it's the same as before. Okay, if you go back, this was our V, so V is still the same. Okay, and so this A is U sigma V transpose. This is the reduced singular value decomposition of the matrix A. This is what it looks like. So this is the reduced SVD. Here, U is a m by n matrix. Okay, it's a rectangular matrix now, tall matrix. V is still the same. It's a n by n unitary matrix. And so U transpose U equals the identity matrix, but U transpose is no longer the identity matrix. It's not even full rank. But V is still a unitary matrix, and sigma is a diagonal matrix, and all the diagonal elements appear in sorted order. Okay, this is the full SVD for comparison. Now, what happens if A were a instead of a tall matrix, you have a wide matrix? Okay, in that case, suppose A were a wide matrix. I don't have the graphics for that, but in that case, U would be a smaller unit vector. Let's look at the full SVD first. U would be a smaller matrix, square matrix, unitary still, in full SVD. Sigma, instead of zeros as the bottom rows, you would have the diagonal matrix and zeros as the right columns. Okay, this white area will be shifted to here, to the right. You'll have a bunch of zeros, the right columns. Okay, and this would be a bigger matrix. It would still be a square matrix, but it would be a bigger matrix. Okay, that would be the full SVD of a wide matrix. And for the reduced SVD, what we have to do is drop the last few columns of V instead of U. As a matter of fact, to get the, if you're given a wide matrix, okay, and you are to find the SVD, all you have to do is take the transpose of the matrix, then determine the reduced or full SVD as desired, and then take the transpose. Okay, that's all there is to it. Any questions? Okay. So this is the reduced SVD, and here all we have done is taken away these last few m minus n number of columns from U, and likewise m minus n bottommost rows of the middle matrix, and then this is the reduced SVD.
Can you treat the transpose thing as again that transpose and then conversion thing? You just share about this transpose, so we can take the transpose and then take the SVD.
Yeah.
So can you repeat that thing again?
Oh, suppose you have a wide matrix.
Okay.
And you want to find the SVD of a wide matrix. Okay, you can directly do it, but you can also take the transpose of the matrix, which would be a tall matrix, and then find out the single value decomposition of that, right? It will be the product of these three matrices or these three matrices. Then take the transpose of the product on this side, and you would get the desired SVD of the wide matrix. Now, let's recall the geometric interpretation of eigenvalues, eigendecomposition, or spectral decomposition, right? So we had the V's were the eigenvectors, they were mutually orthogonal, and V1, V2, V3, they would give the directions of maximum stretching, next maximum stretching, and third maximum stretching, and so on. And how much will the vectors be stretched? Lambda 1, lambda 2, and lambda 3. Okay, so this is the spectral decomposition. Now, when we examine singular value decomposition, it will be a generalized version of this. Okay? So this is our full SVD of A. Okay. Now, A maps a n-dimensional vector to a m-dimensional vector. If you take an n-dimensional x, it's n as a New York dimensional, then y equals ax will be m as in Maryland, m-dimensional. Now let's look at the full SVD. V is unitary, right? So the columns Vi form an orthonormal basis in n dimensions. So any x, any vector x in n dimensions can be expressed uniquely as a linear combination of the Vn's, V1 through Vn. Alpha 1 V1 until alpha n Vn. So that's summation I, alpha I Vi. Agreed? What would be the Euclidean norm of x? Square root of summation alpha I squared. We take the square of all these coefficients and then add them up and take the square roots, right? Why is that? Because these are mutually orthogonal and they are also unit vectors. Okay, now we'll assume that the L2 norm or the length of x is 1. So let's say x is a unit vector. Okay, so in n dimension, x will lie on a unit sphere. Whence alpha 1 square plus alpha 2 square until alpha n square should be equal to 1. Correct? Let's remember all this. Okay, now U likewise is a unitary matrix. So the columns of U also act as orthonormal basis in m dimensions this time. We are dealing with an n-dimensional Euclidean space and a m-dimensional Euclidean space. Okay, we are dealing with two separate dimensions here. X is in n dimensions, y is in m dimensions. Okay, remember that. And we have, fortunately, orthogonal basis vectors for each of our spaces. Okay, now we have already seen this. A equals sigma I ui vi transpose summation of that. Pre-multiplying both sides with vi, we have AVI equals sigma I ui. Kind of reminiscent of eigenvalues, eigenvectors, right? Except this would be V then, and in which case this would be lambda I, right? But that's only in case of a square matrix. Now we are dealing with a rectangular matrix. Okay, so AVI equals sigma I UI. Why? Because VI transpose VI is 1 and VI transpose VJ is 0. The V's are mutually orthogonal and unit vectors. Okay. So X is alpha 1 V1 dot 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 until alpha n Vn, which is summation alpha I Vi, right? We saw that from the previous slide. So what is AX? Y is AX, right? How do we express Y? So X, I replace X with this expression here. So Y would be alpha 1 AV1 plus alpha 2 AV2 all the way until alpha n AVN. Okay. And each AVI can be replaced with a sigma I UI. So AV1 is sigma 1 V1 until AVN is sigma n Vn. Okay. Oh, excuse me. AVI is sigma I UI, so this is sigma 1 U1 until sigma n Un. Okay, so here we have V1 until Vn, correct? AVN, AV1. Okay, now this X is in n dimensionals. So I'm expressing X in terms of the V's, because the V's are basis vectors for the n-dimensional space. And now Y, the product of AX, is being expressed in terms of the basis vector in n dimensions. Okay. What's the L2 norm of Y? I take the coefficients, square them up, and add them up together, right? So L2 norm squared equals alpha 1 sigma 1 squared plus alpha 2 sigma 2 squared until alpha n sigma n squared. Any questions so far? Okay, so this is my X, and this is my Y. I've written down the lengths. Okay? So what's happening? Suppose X were equal to V1. Remember, what's X? X is alpha 1 V1 until alpha n Vn. If alpha 1 equal to 1, then X would be V1. Okay, so let's say alpha 1 equals 1. What is the amount of stretching that you would get? What would be the length of Y? All these terms will vanish. All the alphas except alpha 1 are 0, so it would be alpha 1 sigma 1. Alpha 1 is 1, so it would be sigma 1, right? The L2 norm of Y, I'm showing L2 norm squared, would be sigma 1 squared then. So the amount by which the unit vector would be stretched would be sigma 1. Okay, the directions would change. So this is V1. Remember, Y is the orthogonal basis set for the Y's is this. In n dimensions is U1, U2 until Un, right? And so this Y would then be sigma 1 U1. Okay, so V1 would be the direction of maximum stretching. The amount by which the vector would be stretched is sigma 1, but the new orientation would be U1. Okay, so we want to maximize Y. What we do is let alpha 1 equals 1, in which case X is V1 and L2 norm of AX would be sigma 1. Okay, and sigma 1 is the maximum of AX when X is a unit vector. And B1 is the argmax of L2 norm of AX. Understood? Now we want to choose another direction that's orthogonal to V1 in n dimensions. Okay. So in n dimensions, we want to choose another vector that's orthogonal to our V1 here, this red vector here. And we want to maximize, we still want to maximize, oh, AX is U1, this is AXY is this vector, red vector here. Now we want to maximize AX with this condition. X should be a unit vector, but it should be orthogonal to V1, orthogonal to this red vector here. The answer is, what vector should X be? V2, right? V2 is the answer, argmax of norm of AX, such that X is orthogonal to V1. The amount of stretching would be sigma 2 now. See this blue vector here? This is V2, and it maps to sigma to U2. AX is equal to U2. Sorry, sigma to U2. There's a typo here. This is sigma 1 U1. There's a little typo here. And this is sigma to U2. And so on. Okay, so this geometric interpretation is very much like what we saw with spectral decomposition. Properties. You can see there's a close relationship between the two. Spectral decomposition in terms of the eigenvalues and eigenvectors, and now the SVD. Okay. The columns of V are the eigenvectors of A transpose A. Proof. A equals U sigma V transpose. Okay. This is M by N, M here. So A equals U sigma V transpose. A transpose is U sigma V transpose whole transpose, which is V sigma transpose U transpose. Correct? Whence A transpose A equals this. And U transpose is the identity matrix, because U is a unitary matrix. Here we are looking at full SVD, assuming A is a tall matrix. Okay, so A transpose A will be V sigma square V transpose. This sigma square is actually sigma sigma transpose. Okay, this or sigma transpose sigma. This is slightly informal. Okay, here we are looking at full SVD, if it were a tall matrix. Okay, and now, so this is A transpose A. Okay, this is a symmetric matrix. And look at the the eigen decomposition or the spectral decomposition of A transpose A. This would be a diagonal matrix of eigenvalues, correct? Correct? So, and this is the matrix of eigenvectors. Each column of V is an eigenvector of A transpose A. If you compare this with the spectral decomposition of A transpose A. Why do we have V transpose here instead of V inverse? That's because A transpose A is a symmetric matrix. Otherwise, the spectral decomposition would involve a V inverse, not a V transpose. Okay. Fortunately, A transpose A is symmetric. Okay, so if you compare the spectral decomposition, you can see that the columns of V are the eigenvectors of A transpose A. The columns of U are the eigenvectors of A transpose. Here, again, we take A equals U sigma B transpose, and A transpose is V sigma transpose U transpose, and then we take A transpose, take the product, and that gives us U. This sigma square should be replaced with what? It should be replaced with sigma sigma transpose this time. Okay, instead of sigma square, it should have been sigma sigma transpose, but we are concentrating on the columns of U, so never mind this. So what do we have? Compare this with the spectral decomposition of A transpose, correct? So the columns of U now are the eigenvectors of A transpose. Okay? Singular values, sigma I of A, are the square roots of the absolute values of the lambda i's of A transpose A or A transpose. Okay, well, one of them would be a bigger square matrix, and the other one will be a smaller square matrix. Okay, but they, A transpose A and A transpose would have the same rank, correct? As long as we're dealing with a tall matrix. So what would happen is, which one of these two is the bigger one? A transpose is bigger, right? So it would have all the eigenvalues of A transpose A, but the additional eigenvalues would be a bunch of zeros because they have the same rank. Okay. So the singular values of sigma i's are square roots of the absolute value of the lambda i's of either A transpose A or A transpose. Okay? And we saw it from this. You can take the full SVD here, okay, and then you would get sigma squared plus zeros. When you multiply sigma, the block sigma with the zeros in it, sigma transpose sigma, or sigma sigma transpose, you'll get sigma square, which is a diagonal matrix.
Using this ATA proof that it is equal to V sigma square VT.
Which is this one.
Yes. So it can also be this decomposition utilizing linear equation in pseudo-inverse things.
Yes, you could do that too. Yeah. Okay, next is the low rank matrix approximation. Are there any other questions before I move on to low rank approximation? Okay. So we have a m by n matrix. Okay, and we want to find an A tilde that's very close to A. I haven't formally expressed what I mean by this term closest. But the rank of A tilde will be R, which is smaller than the rank of A. That's why I call it low rank. Okay, so this matrix A, the rank of this would be the minimum of these two, correct? M and N. The rank of A tilde should be less than both M and N. It's of rank R. Let's say R is given to us. Okay, so here's the approach. First the approach, and then we'll formalize it with a theorem. So A equals sigma summation I equals 1 through n of this. Sigma I Ui Vi transpose. So how many terms does this have? N terms, correct? Now, each Ui Vi transpose, I told you, is a rank 1 matrix of the same dimension as A. Okay, now the sigmas, okay, are sorted. So sigma 1 is the highest, then sigma 2, then sigma 3, and so on. So the first term here has the highest weightage, right? Sigma 1 is high. Then the second term, sigma 2, will have the next highest, sigma 2 V2 transpose will have the second highest weightage, sigma 2. Okay, and let's say sigma 20 is 10 to the minus 5 or minus 6, so very negligible. Okay, and then so it will hardly make a difference when we add the corresponding Ui Vi transpose, right? And so this is n terms, and the first term has the highest weightage, the second highest weightage is placed upon the second term, and so on. Okay, so the weightage placed on subsequent terms, they gradually keep reducing. Okay, and so we can drop the last several terms. We can take the first R terms, and each of these is a rank 1 matrix. When you sum up R different rank 1 matrices, you would get a up to rank R. Okay, so we simply drop the last several terms and we take the first R terms, and that gives us a tilde. Okay, and let's formalize this. What did I mean by this closest? One could interpret this as the difference between A and A tilde would be small in terms of the L2 norm. I take the difference between A and A tilde, that would be the error matrix, okay, this, and the L2 norm I want to minimize. Okay, so I want a matrix A prime that would minimize A minus A prime L2 norm, but the rank of A prime will be only R. And the solution is this. This A tilde would be the matrix of rank R that minimizes the L2 norm of the difference. Okay? Now, I will prove this for the L2 norm. The proof for the, you can also take the Frobenius norm here, and this would give you the same result. Okay, but we will use the L2 norm in our proof. So, the Eckart-Young-Mirsky theorem for the L2 norm. Okay, so this is A minus A tilde, summation I equals 1 through n of this minus summation I equals 1 through r. And if I take the difference, I get I equals r plus 1 through n of sigma I Ui Vi transpose. So that's this. I can express this difference between A and A tilde as this. You see, I have the first R sigmas, I've zeroed them out. Okay, I've taken sigma R plus 1 until sigma n. Okay, so this is what the diagonal matrix looks like now. Okay, now what's the L2 norm of A minus A tilde? Note that U and V are unitary matrices. Unitary matrices preserve the L2 norm. Correct? So take a vector, its L2 norm is something, let's say 5, pre-multiply it with a unitary matrix. A unitary matrix is just a rotation of the axes. Okay, pre-multiplication with the unit vector is a rotation of the axes, or maybe involving a flipping also. Okay, but that's all there is. There is no expansion or contraction of x, okay, of the vector. So U and V transpose preserve the Euclidean norm. So we have to take the Euclidean norm of only this. And if you're looking at the full SVD, then there would be a bunch of zeros at the bottom too, correct? But what's the L2 norm of this matrix here? This is a diagonal matrix, okay? The L2 norm, remember this, will be the absolute value, pick the diagonal element with the highest absolute value. And that will be the L2 norm of the matrix. And you can easily prove this. So the L2 norm of this matrix here, or even if you have had a bunch of zeros here, okay, it would be sigma r plus 1, the highest of these, numerically, whichever is the largest. Okay, so the L2 norm of the difference, A minus A tilde, is sigma r plus 1. Okay? So we'll remember this. Okay, so this is my A, and this is my L2 norm of A minus A tilde. Okay, and this is what I'm proving. Now let A prime be a matrix of the same size as A, but of rank R. Okay, now we are considering A prime, any other rank R matrix. And let W be a unit vector such that A prime times W equals 0. Because this is not full rank, right? That's why such a vector W exists. Okay. Now, there are two supposers. I'll explain this in the next slide. Suppose W can be expressed in terms of the first R plus 1 columns of V. So this is my W. W equals alpha 1 V1 plus dot 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 all the way to alpha R plus 1 VR plus 1. Okay. And since this is a unit vector, its L2 norm is 1, so that summation of this alpha 1 square until alpha R plus 1 square should be equal to 1. Now, such a W can easily be found. Okay, such that it can be expressed in terms of the vectors V1 until VR plus 1, but A prime W will be equal to 0. Okay, and the explanation, you can argue this, but I have provided one explanation. So how to find a W in terms of V1 through VR plus 1 such that A prime W equals 0. Okay, V1 through VR plus 1. Okay, so this is expressed in terms, W is expressed in terms of R plus 1 independent vectors, right? And this is of rank R. Okay, A prime is of rank R. A prime W equals 0. So let's take the columns V1 through VR plus 1 and form this V prime. Okay, so this will be, each V is an n-dimensional vector, right? So this is n by R plus 1 dimensions, V prime. And W is a linear combination of these V's. So we can express W as W equals V prime times a vector alpha. This vector alpha contains alpha 1, alpha 2 until alpha r plus 1. Okay, so this vector alpha is a r plus 1 dimensional vector. Makes sense? This is n times r plus 1 matrix V prime, and you're multiplying with a r plus 1 dimensional vector. Okay, so now instead of W, we'll try to find alpha. Let's find an alpha, and then we can use this expression to get our corresponding W. Okay. Now, again, A prime is a m by n matrix, but the rank is R, only R. A prime W equals 0. We need to satisfy this expression. Okay, we need to find an alpha now such that A prime W equals 0 or A prime V prime alpha equals 0. Now we'll find our alpha. And take A prime V prime. What's the dimension of the product? Let B be equal to A prime V prime, and it's a m by r plus 1 matrix, correct? But the rank of B would be R, because this is a low rank matrix, correct? Therefore, and we want to find B alpha equals 0. This is an underdetermined system, right? We have how many rows in B? M, and M is the higher of the two, right? By default, we are looking at a tall matrix. So M, and number of columns of B is R plus 1, correct? But its rank is R. Therefore, how many independent rows do we have? R. Alpha. Okay, and we are trying to find alpha is R plus 1 dimensions, right? So we have n different independent equations to satisfy. N independent equalities, sorry, R independent R, because this has R independent rows, right? So R independent equalities to satisfy, but R plus 1 variables alpha k. So this is an underdetermined system for which we have multiple solutions. In fact, we have infinite solutions, right? We've seen that. Okay, so this is what we concluded from the previous slide, excluding this one, not this slide, but the one before that. Okay, so we continue on with the proof. Now, the L2 norm of A minus A prime is always, by definition, less than equal to A minus A prime, L2 norm of A minus A prime times W, by definition of a matrix norm. So what's the definition of the matrix norm? Find a unit vector W that would maximize the L2 norm of the product, right? So by definition, the L2 norm is L2 norm is the maximum of this with W being a unit vector, right? But we already found a W. So A minus A prime L2 norm of that is less than equal to this, A minus A prime L2 norm of this, A minus A prime times W. Then I open up this, AW minus A prime W. But A prime W from our assumption is 0. So that's AW's A2 norm. L2 norm of AW, okay. So we got this expression here. Now, well, we have it here, actually. W is equal to this. And AW is equal to this. So what's the L2 norm of AW? Is equal to square root of, take the squares of all the coefficients, add them up together. Correct? So this is the L2 norm of AW. Two important expressions that I will use right in the next slide. Okay. Any questions? So these are these two expressions, and I repeat this here. Summation of the alpha I squares equals 1. Now, I want to find minimum of this, right? I want to find an A prime which minimizes my L2 norm of this. And I already showed that this L2 norm of A minus A prime is always greater than equal to the L2 norm of AW, such that A prime W equals 0. Okay. And so this is a lower bound, not a strict lower bound, but a lower bound of this. Okay, let's minimize the lower bound, L2 norm of AW, which is this. Okay. Along with this condition, W should be a unit vector, which means that alpha 1 squared plus dot 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 until alpha r plus 1 squared should be equal to 1. Okay. So this is the optimization problem that I have. I want to minimize this with respect to all these alpha 1 through alpha r plus 1 such that this constraint is satisfied. Summation of the alpha should be equal to 1. This is a optimization problem. What is the solution? Anyone? I want to minimize this with this constraint. Noting that sigma 1 is the highest, and then sigma 2, then sigma r is the next to lowest, and sigma r plus 1 is the lowest, right? So what's our solution if we want to minimize? We want to minimize this. What should we do? This has the lowest weightage, right? Sigma r plus 1 is the lowest of the sigmas. So make this one, alpha r plus 1, equal 1, and set all the other alphas to zeros, right? And so minimum of the L2 norm of AW is sigma r plus 1. Okay, any questions with this? Okay, so this is our solution. So the minimum of this L2 norm of AW is, this is always greater than the minimum, and that's sigma r plus 1. Okay. So the L2 norm of A minus A prime can never be lower than sigma r plus 1, as long as A prime is of rank R. No matter how we choose our A prime, we can never be lower than sigma r plus 1. But we've already seen that A minus A tilde, when A prime is replaced with A tilde, it's of rank R. The L2 norm of that is sigma r plus 1. Whence our theorem is proved. To minimize this, let A prime be equal to A tilde. Okay, so A tilde is the minimizer. And what's the minimum value of this? Not the argmin, but just the min. It would be sigma r plus 1. Okay, so this is sigma r plus 1 is the minimum that you would get. Okay, so this proves the theorem for Euclidean norms. And it can be easily proved for the Frobenius norm as well. Now let's look at low-rank matrix approximation, a demo. Any questions anywhere? Okay, this one is important. This is the main code. This is a subroutine, show the matrices. Okay, so what I'm doing is generating a m by n matrix, A, and then finding out the singular value decomposition of A. This S is that diagonal matrix, and B, by default, it will give you the full SVD. So then I take the diagonal elements of S. Okay, so this matrix, I convert it into a vector. It's a diagonal matrix, right? So this S is now a vector, it just reduces space. So then A tilde, initialize it to all zeros. Okay, and then you see this for loop here. I'm taking the minimum of mn. Well, in this case, it'll be n, 5. So this for loop is going to loop 5 times, and each time to this is initialized to all zeros. What I'm doing is I'm adding a term sigma I or sigma k. I'm using k here. I avoid using I in the for loop because I use as the imaginary number. So I'm using k as the index. So this sk is the sigma k. uk, the kth column of u, and this is the kth column of v transpose. So this is sigma k uk vk transpose. I'm adding to A tilde. Okay. So first iteration, it will be sigma 1 u1 v1 transpose. The second iteration of the for loop, it will be sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose, and so on. Okay. And then I'm showing placing both the matrices adjacently and displaying them in a nice format. Okay, that's all this. So first iteration of the loop, k equals 1. This is A. This is the matrix approximation A tilde. It's a rank 1 approximation. I only took the first term of the summation. And the L2 norm is 80.94. A big error, right? Even the signs are roughly in the right places. 3 negatives here, 3 negatives here, 4. Well, this 50 minus 36. You can do the comparison. They kind of make sense. Well, you have a 16 here and a negative 8 here. Okay, some of them don't make sense, but you can compare. Then second iteration. So A tilde is of rank 2, and the L2 norm has reduced. Now the signs at least seem to be in the right places. Yeah. Oh no, this one, there's a negative 2.5 and a 19 here. But A tilde resembles A more closely now. Third iteration, the norm has, norm of the difference is even lower, and this A tilde upon examination looks similar to this, right? There's some differences. Well, the highest one of them is this is negative 41.2, this is negative 36, but the signs are all in place. Okay, and the differences are not that much actually. 38, 39.9, not 36.4, 38. Okay. Then 39.4, and this is rank 3. Then rank 4 reduced to 23.86 is the L2 norm of the difference. And this A tilde is even closer to A. But it's a rank 4 matrix. What's the rank of A? 5. Last iteration. A tilde is exactly equal to A. Right? So this is summation I equals 1 through 5 sigma I ui vi transpose. The previous one was I equal 1 to 4 and so on. So you see how it converges to A gradually. Okay. Now we can actually apply this technique to image compression. If time permits, I'll explain why the image is being compressed. Okay, so what I'm doing is I'm reading a image. The command for that is JPEG image is mread. Now it will be a matrix. Actually, it will be a three-dimensional matrix because you have R, G, and B. Okay, and then I'm converting it to a grayscale image, RGB2 gray. Okay, but so now it's a matrix, a two-dimensional matrix, and the pixels will be between 0 and 255. 0 for black and 255 for white. Okay, and they will be 1-bit integers. 255 can be represented in 1 bit.
1 byte.
Sorry, excuse me, 1 byte, not 1 bit. 1 byte, right? Anyway, and then I'll convert it to double floating point. And that's why I'm dividing it by 255. So now what I get here is simply a matrix of the same size as the image. Okay, and its values, its entries will be between 0 and 1. Real numbers. Okay. And the size of this matrix is m by n. So the original image was m by n. Okay, and then what I'm doing is show raw image. And that's the command to show the image. This is the image. Original image, and these are the this is the dimensions of the image. Okay.
So the rank would be 697.
697.
Okay.
Now what I'm doing is R equals 5. I'm taking the SVD, USV. Okay. The compressed image, I'm taking only the first R columns of U, first R singular values, and first R columns of V. And R is 5 here. So I'm taking the first 5 terms of summation sigma I ui vi transpose. Okay. And then that's the compressed image. Just like matrices here, this is the pretend this is the original image, and this will be with R equals 4, A tilde would be the corresponding compressed image. This is the original image. After I do this image compression, this is what I get. Very poor quality, right? Rank 5. This matrix is of rank 5. That's why we all see these vertical and horizontal lines, because all the rows, you have only 5 independent rows. Likewise, you have only 5 independent columns. Okay. Then I take R equals 20. This is what I get. Rank 20 matrix. Now it begins to look a little closer to the real picture, but still far off. 50. Okay, even the error, this time I'm using the Frobenius norm actually. If you look at the errors, this was 102, now it's 62, with R equals 50, now it's 39. Now I'm taking 120. Looks pretty good, right? But it's a low rank image. The rank is only 120. not this, what was the original size? Not 697, it's only 20. 120. Then 250. You practically see the whole image. 400. This is the error. And this is the original. Practically no difference, right? Now, why do I achieve image compression? Okay, to store the whole image, it would take this many spaces, right? This is a large number. Let's do 250. So, how many column vectors do I have? Independent column vectors.
250.
250, right? So each UI, so we have 250 UIs and VIs. The UIs will be of dimension 697. So to store all the UIs, let's say we're taking R equals 50. 697 times 50 to store the UIs. To store the VIs, 1216 times 50, not 697 times 1216. It'll be, the total size will be 697 plus 1216 times 50. Okay. Correct? Well, we forgot the sigmas. So another 50. So 697 plus 1216 plus 1 times 50. That will be a much lower number, right? So you are actually using a lot less space. Let's say with R equals 250, you still do the math, but you still might save space. Okay, but you get something that is visually indistinguishable from the original. Yeah. Well, 400. I don't know with 400 whether you'll get image compression or not, but indistinguishable, and this is a minor degradation, I think. Okay. So image compression can be achieved, and it can be used for image transmission too. Question?
But my question is, by going in the low rank approximation, we can achieve the image compression. Mm-hmm. We can save the memory, but
or transmission.
Yes. But we are also affecting the quality of the image as well.
Well,
we are moving from high definition image to low definition image, isn't it? And can we also regenerate the low definition image to the high definition?
Of course not. Of course you cannot. That's permanently lost.
Okay.
But here we can exploit the human ability to distinguish between different shades. Okay, maybe for a human being, 400 with this is indistinguishable from this, right? So, and I'll give you the code. I'll upload it to the course homepage. So anyway, we saw the full SVD. This is what it looks like. And this is the reduced SVD. And we saw that we can decompose A into summation of rank 1 matrices. And if we take an X like this, our AX would be looking like this. And so this is part of the geometric interpretation. The L2 norm of X is this. This is the L2 norm of AX squared. This is what happens with SVD, the geometric interpretation. These are all unit vectors. and they map onto this ellipse here, and this is in how many dimensions? N as in New York. This is in M dimensions, M as in Maryland, right? And so V1 is the vector, unit vector that yields the highest stretching, and this is sigma 1 U1. V2 is the one that yields the second highest stretching, that should be orthogonal to V1, and the amount of stretching is U2, and the vector would be, sorry, the amount of stretching is sigma 2, the vector is sigma 2 U2, and so on. Okay, and so you can compare this to spectral decomposition. And we've seen these, the SVD of A transpose A, or rather the spectral decomposition of A transpose A and the spectral decomposition of A transpose. From these, we can compute the columns of U's and V's and the singular values of A. And we've seen the low rank approximation. We saw the Eckart-Young-Mirsky theorem for L2 norms. And like I said earlier, you can extend this for the Frobenius norm as well. Here, the L2 norm of the difference is replaced with the Frobenius norm. Okay? Any questions? Anywhere? This was an interesting application, right?
Yeah.
Okay, so we end today's lecture. I won't have a office hours today.